This is M12Q7. The question is asking about the game theoretical value of a matrix form or a normal form zero-sum game. And the problem is I never talked about this in the lectures. So the definition I gave is basically the value of a game is the value of the solution of the game. So here is the value of a Nash equilibrium. It turns out that this definition is not a great definition because not every game has a Nash equilibrium. So in those cases, we don't know the value of the game. So I'm going to talk about Professor Drew's definition as well, which is what I usually call the minimax payoff definition. And it's supposed to be min-max payoff, but someone added an I in between for no reason. But well, it sounds cool, so I'm okay with it. And in any case, the payoff is defined as just you maximize the number in each column and you take the minimum of those numbers. So I will talk about this later. I'll first talk about my definition, which is just finding the value of the Nash equilibrium. So hopefully at this point, you know how to find the Nash equilibrium. It's basically finding the best responses. So suppose the column player is playing action 1, then the best response of the role player, because the role player is the max player, the role player is trying to maximize the payoff here, and the maximum of these three numbers is 1. So the best response is basically action 2. And similarly, we can find the best response if the column player is playing action 2, circle the largest number in the column and circle the largest number in the column. So these things are called best response of the role player given the column player's action. And we can do the same thing for the column player. So if we know the role player is playing action 1, then the column player is the main player. So the column player is trying to minimize the payoff. So here the minimum is 0. And in the second row, so if the role player is playing action 2, then the minimum of 1 to 1 is 1. So highlight both of them. And last row is -7. So these are called best response of the column player given the role player's action. So there's one cell with both numbers highlighted, the same number highlighted twice. It means it's a mutual best response. So 1 is the best response of 2, and 2 is the best response of 1. And by definition, that's a Nash equilibrium. And the value should be 1 here. So that's our first approach. Let's look at the second approach. So as I explained before, minimax payoff is just the max along the columns and take the mean of those numbers. So the max along the first column is 1, along the second column is 2 and 2, along the third column is 8, and you can probably notice this is just the best response of the role player. So it's the same thing, but the next step is different because we're just minimizing among these numbers. We don't care about the best response of the other player, and it's the minimum of these 4 numbers, and it's 1. So this is 1. It seems a lot faster, but let me go through another version, which is the maxi-min thing. No one's calling the maxi-min. It's just max-min payoff. So you can minimize the payoff along each row and just take the maximum. So here, minimum is 0. Here, minimum is 1 and 1. Minimum is -7. You can notice again, this is just the best response of the column player. But in any case, just take the maximum of these 4 numbers. And it's just 1, so it's 1 again. So all these 3 approaches agree. You may think maybe it's lucky, or maybe it's because there's only one Nash. So I want to give you some intuition why it's more general than that. So let me use some made-up example. So suppose we are using the max-min approach, and we have the minimum along each row is, say, it's x and y and z. So we need some ways to name these actions. So let's call them A, B, C, and let's call them 1, 2, and 3. So we will make assumption which one is the largest one. So suppose, say, y is the largest one. So y is larger than x and y is larger than z. So what I will try to show you is if this is the case, then z and x, these two cells will not be Nash equilibrium. And this, I think it implies either this cell is a Nash, then y is the value anyways, and it's consistent with these two definitions are consistent, or none of these are Nash equilibrium, so we don't have a Nash. So let's try to go through the derivation. So we want to show that basically z is not a best response for one of them. We already know that z is the minimum, so this number is larger than z, this number is larger than z. So this is the minimum, so we already know that the 3 is the best response for the column player given the row player is playing C. So we want to show that the best response of the row player given the column player is playing 3 should not be C. So we just need to figure out if this number is, say, larger than Z, then we're done. And we actually know it because we know Y is the minimum in the second row. So this number is larger than Y, and this number is larger than Y. And we also know this relationship, Y is larger than Z. So this number is larger than Y, and Y is larger than Z. So in particular, this number, whatever this number is, it must be larger than Z as well. So basically, the best response cannot be this, so that's why this is actually true. Okay, so we can go through the same thing again for x. So we want to show that x is not the best response. So what we're doing is fixing the column player playing action 1, and because this number is larger than y, and y is larger than x, so this number definitely is larger than x. So the best response should never be A because B is better than A. So this is not the best response. So the best response should not be equal to A. So we cannot have this cell as a Nash equilibrium. So now we show that if there is a Nash, it must be Y. So that basically concludes if there's more than one Nash, the only way is to have Z and X actually equal to Y. But in any case, the game theoretic value is consistent with our min-max definition, which is equal to Y in this case.